Hello, everybody. All right, so we are moving on. So we just got finished talking about antiderivatives and differential equations. And so now we're going to really start getting into the actual integration piece. So this is our final unit that we will talk about for this school year, and it's integration. Now, it's not as big as derivatives because pretty much you're just going to be doing the same thing that you do with derivatives, except you're going to go backwards. But there are a few different things, like what we're going to talk about today, that is not typically um, like what you did in derivatives. So they're a different way of doing estimations. So we're going to start off with Riemann sums. And so what we're going to do is we're going to look at approximating the area under a graph using one of the four methods. Actually, we're going to use two of them because we're going to use left and right. And then we're going to also look at if we have an underestimate or an overestimate as we're going through this. So this section, there's a lot of different things, but we're going to start off with the small one first to get you eased into it. And then from there, add the rest of it into the Riemann sums piece. So we are going to look at, oops, I missed one. Maybe I didn't. Okay. We're going to look at estimating area under a rectangle, under a curve using four different methods. We're going to use rectangles. We're going to use the midpoint rule, and we're going to use the trapezoid rule. And through all of this, we are focusing on one main thing, which is our Riemann sum. And so as we go through this, we're going to have other topics that are going to relate to Riemann sums here. So that relates to this one. We're going to start here with this one, and then later we're going to go to midpoint, and then we're going to go to trapezoid. So we're going to start with rectangles because that's the easiest, because everybody knows about rectangles. So we have this curve here. And our job is to be able to find the exact area under this curve. Well, in a few weeks, maybe not even that long, you'll actually be able to do that. But for right now, we're going to estimate the area under this curve. And we can do this by using rectangles. And so the nice thing about rectangles is everybody knows how to find the area of a rectangle. Length times width, you're done. The key is when you're trying to find the area under a curve, you want to use as many rectangles as possible. Now, I can't tell you to use an infinite amount of number of rectangles because you're not going to first off be able to draw them that small and figure out the width and the height and everything else. However, what's going to happen is you're going to be given an interval like 0 to 3 and something, and they're going to ask you to find the area or estimate the area under this curve, using three uniformed rectangles. And so as we go through this, you're going to see actually what I'm talking about here when we're talking about uniform versus non-uniform. And then we're going to talk about estimating and non-estimating and everything. And so if you take a look at these three pictures here, if you noticed, like on this first one here, we're trying to find the area under this curve. We're going to estimate, and obviously it's an estimation because if you look, even though I have these three rectangles here, I have all this empty space. And so when I'm looking at this and I'm trying to estimate this one over here is going to be a much better estimate than this one over here because we have all this open space right here. And so when we estimate, again, you want to use as many uniformed rectangles as possible. However, again, it's not going to be feasible to do that. And so that's why that's why this is an estimation versus an exactness, because regardless of however many rectangles you actually wind up using, you're always either going to be over or under the actual specific area of what's under that curve. And so if we look here on this first one here, I've got these four rectangles. So you might see a problem that says find the area under this curve when your n is equal to 4. And so what this is telling you is that your n, that's how many rectangles they want you to use, and they want you to be uniformed. And then you'll notice too, while we're on this, that each one of these rectangles touch the actual curve. And so that's also what's going to name what you're going to be doing. So if you're looking at this specific problem here, if I'm looking at this one right here and I'm saying, okay, I want you to use 4 uniformed rectangles, and I want you to use what's called a left Riemann sum or a left rectangle. And I'm saying, left here because if you take a look here at each one of these rectangles, the left corner of each one of these rectangles actually touches the graph that we're questioning here. And so that's why this would be considered a left Riemann sum, because the left portion of the rectangle is actually touching it. And so as we look at these 3 graphs, it's the same graph here. And again, the more rectangles you use, the less space that you actually wind up having. So that's what a Riemann sum does. It helps you with that approximation. And what we're eventually going to do is we're going to take these Riemann sums and then we're going to be bounded. Like, okay, so what is this? What is the lowest amount that we could possibly be okay with? And what's the highest amount that we could also possibly be okay with? And your exact amount is going to be somewhere right in the middle of those two. So again, as we move forward, you're going to see how this all comes into play. Okay. So when all your rectangles, I just talked about this, when all your rectangles touch the curve that you're looking at with the left top corner, this is your left Riemann sum. So what you're going to do is you're going to find the area of each one of these triangles here, and you're going to add them up, and that's going to be your estimate with a left Riemann sum. When it says uniformed, what uniform means is that your x's have the same width all the way across. So basically the base of the rectangle, they're all going to have the same width. It's the height, the y value, that's going to be the different piece. Okay? And so that's what you kind of need to keep in mind as we're going through this. When you're taking a look at this, we're taking a look at the fact that, okay, that if I'm uniformed, my x values, my width, my delta x, there we go. My delta x is always going to be the same width. And then my y here, my height here, that's actually what's going to change every time we go through this process. Okay. So you take a look at this here. This is your left Riemann sum. Same picture, except now we're going to look at a right Riemann sum. So when you notice we have the same graph here, when we're using a left and a right, you will notice that with the left one that we have an underestimate because we have all that open space, but with the right, we don't have any open space, but we have all this triangle stuff that's above the actual graph right here. So that makes us have an overestimate. And so when you take a look at the left and right together, that's where those boundaries come into play. Now, it's not always going to be, well, if you have a left Riemann sum, you're going to have an underestimate. If you have a right Riemann sum, you're going to have an overestimate. It also is going to depend on the graph itself, whether it's increasing or decreasing. So before we go to that, take a look at this. Is this going to be a left Riemann sum or a right Riemann sum? So if we look at our graph right here, we see that our graph here and each one of our rectangles, well, if we take a look, the right corner is touching the actual graph in question. So therefore, we have a right Riemann sum. All right. So this is how you're going to figure out if you're going to have an overestimate or an underestimate and how it's actually going to wind up happening. So if you are increasing, so if your function is, as x gets bigger, my y gets bigger. So if that's happening there, if you're going to be using a left Riemann sum, you're going to have an underestimate. And then if you use a right Riemann sum, you're going to have an overestimate. And then the reverse is true. So if you have a decreasing graph, so as my x gets bigger, my y gets smaller. that means that now your left is going to be an overestimate, and then your right is going to be the underestimate. So it depends on, basically, is my graph going positive or negative. So that's what you have to kind of keep in mind as you go through this. All right. So when we're dealing with Riemann sums, you're going to hear the words subdivision. You'll hear the word partition. What this basically means is, how many rectangles do they want? And when they say, I want you to take this interval and I want you to partition it, 6 different ways, that means it wants 6 uniformed rectangles. So you need to take your interval and divide it up appropriately to be able to figure out how many, figure out what your width of each one of those rectangles is going to be. And then the height will come once you get ready to plot those actual points. So again, your subdivisions, your partitions, whatever they want to call them, that's how many rectangles you're actually going to wind up having. Now, we can have uniform, which is traditionally the most common. Uniform rectangles is the most common type of rectangles that you're going to use. But there are opportunities to have non-uniformed, and non-uniformed usually means that you've got something that looks like this graph over here. Now, when we talk about non-uniform, 9 times out of 10, it's going to wind up being in a table. So as we're going through these and we're taking a look here, whatever, your non-uniform ones will probably come off a table. They're probably not going to ask you, giving you a graph and telling you, give me, 3 non-uniformed rectangles. That's just probably not going to happen. So it's typically, you're going to see it in a graph. However, I'm sorry, not a graph, a table. But however, in a graph, 99% of the time, it's going to be uniformed. Okay. So that is what you're taking a look at here, uniformed versus non-uniformed. So what is the correct description of the subdivisions of this Riemann sum? So if I'm taking a look here, well, if I notice that everything looks the same, it looks like they're the same width, so I can go ahead and get rid of all my non-uniformed ones. And then I've got 1, 2, 3, 4, 5, 6 different rectangles. So my answer is 6 uniformed subdivisions. All right. Now let's actually jump into a problem here. So imagine I give you this graph and I want you to approximate the area between this graph here and the x-axis from 2 to 6. And I want you to use a left Riemann sum. So what you're going to do is you're going to come over here and say, okay, a left Riemann sum. That means I'm going to start here at 2 and I'm going to go all the way up and I'm going to put a dot right there. And then that's where I'm going to start at, because I'm doing a left Riemann sum. So now we got to figure out, all right, well, how am I actually going to wind up doing this? Well, since they didn't really give you anything, you kind of get to make your own decisions. And I would go ahead, and since we're looking at, I don't know why it keeps jumping like that for. Since we're looking at this, just go ahead and make everything a width of 1. So that means I'm going to come here and I'll go this way and then down. So there is my first rectangle. And then I'm going to go up here to 3 and I'm going to do the same thing. And then I'm going to connect it here and I'm going to go over and I'm going to go down. And then I'm going to go to 4. Now I'm going to do the same thing, over and down. And then I'm going to go to 5, do the same thing, and I'm done. So I'm going to be looking at these rectangles as I'm actually going through this problem. So if you want to take a look at, that's actually what I'm going to be looking at and how I'm actually going to be doing this. And I'm going to be doing a left Riemann sum, so that means each one of my rectangles, the left corner of that rectangle is actually touching the graph. So once I draw that out, I need to find the area of each one of these. So this is what I know. I know that my width for each, because this is uniform, is going to be 1. Because from 2 to 3 is 1, 3 to 4, 4 to 5, 5 to 6. And so now what I need to do is I need to figure out the height. Well, I've got a 3 here, and then I've got a 7 here, and I've got a 6 right here, and I've got a 4 right here. So now what I'm going to do is I'm going to take my width times my height, and then I'm going to wind up doing this. So I take my width, which is all ones, my height here. I have all, so then I multiply it using the length times width. And then what I'm going to do after that is then I'm going to take these answers and I'm going to say, well, 3 plus 7 plus 6 plus 4. So my area is approximately 20. But 20 what? You can't have a naked answer. You have to have something. So since we're talking about area, your answer will be 20 units squared. So 20 feet squared, 20 centimeters squared, 20 miles squared, whatever it is 20 something squared. So if it doesn't have anything, then you need to make sure you're putting something in there like a U for units. All right. So take a few moments. We're going to approximate the area between h of x and the x-axis from -2 to 4. And we're going to use a right Riemann sum with 3 equal subdivisions. So I'm going to give you a few moments to let you actually go through this, and then we're going to talk about what you came up with. So hit the pause button now. All right, here we go. So we need 3 equal subdivisions from -2 to 4. So the distance from -2 to 4, that is going to be 6. So that's my distance, which means since I need 3 of these, I'm going to take that distance divided by 3. So each one of my widths is going to wind up being 2. So I've got 2 times something, 2 times something, and 2 times something. I know this is really blurry, so we're going to try to walk through this here. So if I start here at 2, I need the right portion of it. So that actually means I'm coming over here and I'm drawing it down. Oh, no, that's a 1. My bad. Let's try that again. So I'm starting at 2. Let's do it this way. Since I can't really see it that well. We're going to start over here with this 4. We're going to go right here. And I want to go a width of 2. And we're going to come down like that. And then we're going to come here. And I've got that. We're going to come over. And we're going to come down like this. And then I'm going to come here, which looks like it's about right here. And then I'm going to come over and I'm going to come down like that. So what I'm going to do is I've got a height here of 1, 2, 3, 4. And then here I've got 1, 2, 3, 4, 5, 6. And then here I've got 1, 2, 3, 4. So I wind up with an 8, a 12, and an 8. And when I add all that together, I get 28 units squared. All right. Yeah, so that one's kind of hard to do, or look at. So here's a I guess a helpful tip. helpful tip. When you're doing left and right, whatever side it says that you should be doing, like if you're doing a right Riemann sum, start from the right side and then work your way left. If you're doing a left Riemann sum, start with the left side and work your way right. That way you're not trying to figure out, okay, where do I actually start this thing at? You're starting it, you're just going to start it going backwards. So because it's the right, we started in this direction over here and we worked our way into that direction and make sure that we had our 3 equal subdivisions and that every right corner of these rectangles are actually touching. All right. Excuse me. All right. But what if we don't have a graph, Miss Calvin? I don't get it. All right. So if we don't have a graph, that's okay because you can use the table to do the same thing. The only difference is are you going to look at where you're going to look at your y values at. So this is not that big of a deal. So it's actually a little bit easier than what it looks like. So imagine that we're asked to approximate the area using a right Riemann sum with 3 equal subdivisions. And we have to use this table right here to help us find our answer. So we have everything that we need right here. The key is how do we read this graph? Okay, so we need to first off figure out our width. So we need to make sure that we're doing that. So did it tell us how many rectangles to use? Yeah, so this one says 3 equal subdivisions. So I gave you a little bit of help here. So the first thing you want to do is we want to make sure that we divide the interval into 3 or however many they're asking. But in this case, it's 3 different rectangles. And then we're going to evaluate each endpoint at that x value. And then since they told us right, in this case, we're going to use the right Riemann. And then we're going to actually find the area of each rectangle and add those sums together. So that's kind of the steps that we're actually going to do as we walk through this process. So 1 to 10 here. So the nice thing about this is if I go from here to here, that's a 3, that's a 3, and that's a 3. So we know that the length of each one of these rectangles is going to be 3. The question is what about the height? So since we're using the Riemann sum, the right Riemann sum, we're going to read this going from right to left. So we're going to read this going in this direction. And so you have to visualize these actual rectangles as they're being put on here. And so this going in this direction, we're going to be using these 3 numbers, 5, 3, and 8. Because we're using a right Riemann sum, this is the right top corner of the first rectangle. This is the right top corner of the next one, and this is the right top corner of the next one. If we were using left Riemann, which we're not for this problem, but if we were, then we would use these 3 instead. So when you're looking at a table, your starting point is the crucial point. If you're using right, you're going to start with the right and work your way left. If you're using left, you're going to start your way left and work your way right. So we have the length of 3 in each one of our heights. So now what we're going to do, oh, we didn't finish it. So now we come over here and say, okay, I did that. We're going to multiply each one of these times 3. So that's 15 and 9 and 24. So that's 18, carry my 1. That's 48 units squared. So that is what the answer to this one would be. So when you're looking at a table, depending on if it's left or right, that's the hardest part to figure out. Remember, if it's right, you're going to start from the right for the y values only. And then if it's left, you're going to start from the left. And if you take a look here, and that's one of the reasons why I drew this too, if I'm starting from the right, there's my top, and then there's my top. That's my top right corner. If I was going left, it would be the opposite. Okay. All right, so take a few moments, try this problem out here. We're going to go from 10 to 16, and I need 3 equal subdivisions with a left Riemann sum. So go ahead and hit your pause button now. All right, welcome back. Let's see how you did. So there's that one and that one and that one. So there's our 3 equal subdivisions. So I have 3 rectangles here. And the width of each is going to wind up being a 2. Okay. I'm doing a left Riemann sum, so I'm going to use these 3 numbers here. I'm going to multiply those. And then I'm going to add them together. And there you go. All right. Hopefully it's not too bad. It doesn't look as bad as you think it is or whatever else. So hopefully you're going, okay, yeah, I get this. It makes sense. All right. So what if I give you nothing except an equation? So we want to approximate the area between -3 to 3 of f of x is equal to 2 to the x. And we want to use right Riemann sums with 3 equal subdivisions. So if I'm going to go through this here, basically you're going to make a table. So the first thing you need to do is you're going to go from -3 to 3. So if I'm going from -3 to 3 and I'm using 3 equal subdivisions, so that means my distance is 6. I've got 3 equal subdivisions, so that winds up each interval or each width of the triangle needs to be a 2. So we start at -3, and then we go to -1, and then we go to +1, and then we go to 3. So those are our x values. And then we have our f of x values. Now we evaluate. So when you put a negative, don't forget this turns into a fraction. So 2 to the 3rd power, that's going to be 8, but it's a negative, so this is 1/8. 2 to the 1st power is 2, but it's negative, so it's 1/2. And then we have 2, and then we have 8. We're looking at right Riemann sum. So we have 2, 2, and 2, which means I'm going to use this one, and that one. So I have times 8 times 2 times 1/2. That gives me 16, 4, and 1. So I wind up with 21 units squared. So if they don't give you the graph, make your own table. Simple as that. And again, draw your rectangles if you need to, so that way you can see what you're actually looking at when you're dealing with this. You know that you're dealing with the right Riemann sum, so you know those are the ones, those 3 up there are the ones that you're actually going to need to use. All right. So finding the area under the curve. So same thing. I'm going to give you a few moments to do this one. Estimate the area under the curve of y equals 1 minus x squared from 0 to 1 using 4 rectangles. So what I want you to do is they want you to find the area of this. So yeah, go ahead and pause the video and give me a left and a right on here, and then when you come back we'll actually walk through it and see how you did. So go ahead and pause it now. All right, so let's see how you did. All right, so what we're going to do is we're going to estimate the area in the curve. So basically I'm bounded here from 0 to 1, and so I want to figure this out. So the first thing I need to do is, again, I need to figure out, well, what is that delta x? So that width that we've been finding, the width of each one of those, that's actually called delta x. And so I just need to figure out what the distance is. Well, from 0 to 1 is 1. And I need 4 subdivisions. So since I have 4 subdivisions, I'm going to wind up doing this. So my delta x is going to be 1 minus 0 divided by 4, because that's how many rectangles I want. So each width of my rectangle needs to be 1/4. So that means my intervals that I'm going to use are going to look something like this. And so now, when I'm doing this, I've got this popping up that looks like this. So notice here that this is a left Riemann sum. I'm decreasing. So that means since I've got a left Riemann sum and I'm decreasing, this is going to be an overestimate. And then I just need to basically find the height of each one of these rectangles. So that's where this piece comes in here. Did I do that already? So you're going to create your own table. We know it was 0, 1/4, 1/2, and 3/4. So that's for your left. That's all we care about. So we wind up with the 1 here. And then we go for the 1/4, 1 minus 1/4 squared. That's going to be a 16. So this is a 15 over 16. Then we have 1 minus 1/2 squared. So that's going to be a 1/4. So it's going to be 3/4. And then we have 1 minus 3/4 squared. So that's 16 again. So we have 16 over 16 minus 9 over 16. So that's 7 over 16. So this is what the left endpoints are going to look like. Did I do that here? I don't remember. Oh, maybe not. So with our left endpoints, again, we just went through this. And then, so since we're only focusing on the left, I go through here and say, okay, well, I know that for my left here, I'm going to use this one, this one, this one, and that one. I don't care about the last one. So I take my width is 1/4, my delta x, times my height. So 1 times 1/4 plus 15 times 1/4, so on and so forth. I get this line here when I clean that up. And then I just keep walking it down, okay, until I get something I can work with. So the approximation for my left is going to be that piece right there. When I do my right endpoints, I'm going to use the same table, except now I'm doing right. And I don't care about the first one. So the same thing. I'm going to walk it all the way through. And I wind up with that piece right there. So when I'm looking at what the possible answer could actually be, I have an underestimate and an overestimate. So I put them in an interval notation form. So this would be an estimation that I would be happy with when my n is equal to 4. I am happy with this estimation. I know that the actual answer is somewhere in between there. So I am good to go on that. Now, in probably about a week or so, you'll actually be able to find the exact answer to this question. So file this somewhere, because we're going to come back, take a look at this, and I'm going to show you exactly how to find the actual answer to this. Okay. All right. So this kind of puts everything together. So I want you to take a few moments, and I want you to pause the video, and I want you to do all of this here. And then when you're ready, hit resume, and then we will actually go through the problem, and then I'll tell you what to do next. All right, so go ahead and hit the pause button now. All right, here we go. Let's check your answers. So if you take a look at this, so we know our delta x is 1/2. I know we're going from 1 to 4, and we're trying to divide this into 6 different intervals. That's kind of ugly, but that's what we're doing. So yeah, so we're going to go through here from 4 to 1 and 6 different subintervals. That means everything is going up by 1/2, but we're going to start at 1 and end at 4. So when you go through, and I know these are hard to see, but this is where everything kind of gets split up at. Is right there, just like that. So then you wind up with this following table right here, which is nice. So then we're going to find the right endpoint. So with the right endpoint, I'm starting over here. And we're just, again, going to walk all the way through this with the right endpoint here, 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 and here. So as you're going through this, here's your delta x that keeps popping up right there. And you're just multiplying that delta x times each one of those y values, cleaning it up, and you wind up with an answer that looks like that. With the left one, you're going to use these values here with the left one. And then again, go through, clean it up, and you wind up with something that looks like that. And so when you actually write if you want to write like an interval notation form for our 3 decimal places is where you round to. So 1.2, 1. Oh, it's like, why is that there? Like, that's weird. Let's try that again. 1.218 is less than or equal to the actual answer, which is less than or equal to 1.592. Oh, that 2 is 3. Okay. All right. So with that being said, that's your introduction to Riemann sums. So now what I want you to do in Google Classroom, your worksheets are up, and then we'll go through some more problems that look like this. So if you have questions, make sure that if I'm not around, you're hopping on Google Classroom or you're sending me reminds or whatever else. But yep, that ends the first part of Riemann sums. So I hope everybody is having a great day, and I will talk to everybody soon. TTFN. Ta-ta for now.